Okay, let's dive in. So, these large language models, they're doing just incredible things these days, right? Tackling tasks we wouldn't have even thought possible just a few years back.
Absolutely, the capabilities are amazing.
But there's always a catch, isn't there? And the big one here is that these models are massive.
Huge. Billions, sometimes trillions of parameters. Think of them like the connections in a brain.
And all that size means they're really expensive, very resource hungry to run, especially at scale.
Yeah, exactly. Trying to deploy, say, a GPT-4 level model for every single little task everywhere. The compute cost would just be astronomical.
It's just not practical for a lot of applications.
Not at all.
So naturally, people are looking at smaller models. They're cheaper, faster, you can run them on less powerful hardware.
Makes sense.
But the problem is, how do you get these smaller models, and we're talking maybe hundreds of times smaller, how do you get them to actually perform well on complex stuff? Things needing deep reasoning or, up-to-date knowledge?
Right, on their own, they often struggle with that. They fall short.
And that's really the core challenge this paper we're looking at today tackles.
Yeah, there's already been quite a bit of work trying to train these smaller models by basically copying the thinking process of the bigger ones.
Like the chain of thought, Coty, distillation.
Exactly. You take the step-by-step reasoning from a big LLM teacher and you sort of distill it down. You're essentially teaching the small model to mimic the teacher's internal monologue. Like, okay, first I do this, then this.
So the small model learns to generate that whole sequence of thoughts before the final answer. It learns the trace of the reasoning.
Precisely. And look, that does help. It definitely improves their reasoning compared to just spitting out an answer.
But as this paper points out, just mimicking that static reasoning trace, it's often not enough.
No. Because if the problem needs information the small model hasn't memorized, or maybe needs a precise calculation it can't quite handle reliably, well, it often just fails. Or worse, it starts making things up, hallucinating.
Like that example they give in the paper asking, what would $100 invested in Apple stock in 2010 be worth by 2020?
Right. A small model using just Co might try to reason it out step by step, but it doesn't actually have the historical stock data stored inside, and it might mess up the calculation too.
So it's trying to solve this dynamic problem, needing real-world data and calculation, but it only has its static, maybe outdated internal knowledge.
It lacks that ability to, go look something up or use a calculator.
That's the key limitation then. They're learning to repeat a sequence of thoughts, but they aren't learning how to actually interact or use tools when their internal knowledge hits a wall.
Exactly.
All right, so if just distilling the thought isn't the whole picture, how do you teach a smaller model to actively seek help or use tools? This paper, Distilling LLM Agent into Small Models with Retrieval and Code Tools, sounds like it has an answer. They call it agent distillation.
This is the core idea. Instead of distilling just that static reasoning trace we talked about, they distill the full behavior of what they call an agent.
An agent. What does that mean in this context?
Well, think of an agent as something that observes its environment, thinks about what to do next, takes an action, and then sees what happened. It's a loop. Reason, act, observe.
So like teaching it to be a little digital problem solver, one that can interact with things outside itself.
Exactly. And the actions here are specifically about using external tools.
Okay.
Like a retrieval tool, think a search engine to find information, and a code execution tool to run calculations or other bits of code.
Got it.
Agent distillation trains the small student model to mimic the big teacher agent's entire reason, act, observe cycle. That includes when and how to use these tools effectively.
So the small model isn't just learning the answer or even just the steps the teacher took on paper, so to speak.
Yeah.
It's learning the skill of knowing when it's stuck, figuring out which tool it needs, how to actually use it, and then taking that result back into its thinking process.
That's the fundamental shift.
Yeah.
And the advantages are pretty clear. The small model doesn't need to memorize everything under the sun. It learns the skill of finding and using information or performing calculations when needed. And this means it should generalize much, much better to new problems. Problems that need facts or calculations it's never explicitly seen during training.
That really does make a lot of sense. It's learning a dynamic process, not just a fixed path. So the big question they tackle in the paper is, can you actually transfer this complex interactive agent behavior from a really big teacher? They used a 32 billion parameter model, right?
Yeah, 32 billion.
Can you get that behavior into something way smaller, like models down to 500 million or 3 billion parameters?
That was the key hypothesis. Can this really work across such a size difference?
Okay, training a small model to do all that, the reasoning, the acting with tools, observing it, sounds pretty complex. Did they run into any specific problems trying to make this agent distillation work, and how did they get around them?
They did highlight two main challenges. First, teaching this interactive reason act observe pattern is, well, different from typical instruction tuning. Standard tuning is often more about static input-output pairs or just generating text sequentially like in a coast trace. This agent stuff with actions and observations, it can be a bit outside the usual data distribution these models are trained on.
Right, because the agent's actions and the observations it gets back aren't just plain text in the same way.
Exactly. And the second challenge is about the tools themselves, especially the code tool. Even if a small model has seen some code, getting it to consistently generate functional, error-free code when it's acting as an agent, that's tough.
Yeah, I can see that.
An agent's code action needs to run properly to get a useful observation back. Small models are just more likely to make syntax errors or use the tool's interface incorrectly.
So if the code bombs out, the whole agent cycle breaks down right there. How did they try to tackle these issues to make the distillation better?
They came up with two methods, actually pretty simple concepts, but quite effective, it seems, to enhance the process. The first one is called First Thought Prefix, or a FTP.
First thought prefix.ftp. Okay, what's that doing?
Well, they noticed something interesting. When you prompt a big teacher LLM to act as an agent, its very first thought might be quite direct, maybe immediately jumping to the first action it wants to take.
Okay.
But if you give that same big LLM a standard GoP prompt, like let's think step by step, it often starts differently. It might begin with a more structured planning type statement, something like, okay, to solve this problem, first I need to figure out X.
And that more structured start, that planning bit, seemed helpful for the overall quality of the reasoning.
Yes, it suggests that having a deliberate planning phase up front is good for tackling complex problems. The issue was that the teacher agent, left to its own devices, might skip that explicit planning thought when generating the training data.
Which could lead to less ideal training examples for the student model.
Potentially, yes. Less optimal trajectories.
Yep.
So the first thought prefix method basically takes that helpful first structured reasoning step you'd get from a copy prompt and sticks it onto the beginning of the teacher agent's actual first thought when they're generating the training data.
So you're kind of nudging the teacher agent to start its thinking with that more structured planning approach.
Exactly. It's like giving it a little prompt itself to encourage that planning mindset, which seems beneficial. The goal is to create higher quality demonstration trajectories for the smaller student to learn from.
That's clever. And you mentioned, importantly, this prefix is only used when generating the training data from the teacher, right? The student doesn't see it when it's actually running.
Correct. It's purely a training data enhancement technique for the teacher's output.
Okay, that handles improving the training data quality. What was the second method? You said it addressed the action errors.
Right. The second one tackles the problem of the small distilled agent generating invalid actions, especially that non-functional code. This method is called self-consistent action generation, or SAG.
Self-consistent action generation, SAG.
Is that like it double-checks its work before acting?
Sort of, yeah. This happens at test time when the small agent is actually trying to solve a problem. Instead of just generating one single thought action sequence and hoping for the best, it generates multiple possibilities.
Exactly. It samples multiple potential thought action sequences for that step. It explores a few different ways it could think and act next.
Okay, so it has a few options on the table. How does it pick the best one?
Then it uses a lightweight code interpreter, or whatever tool feedback mechanism it has, to actually check if the proposed actions in those sampled sequences are valid. Does the code run? Does the search query make sense?
It tests them out.
It filters out any sequences where the action was invalid or produced an error. Then, for all the sequences where the action did work and produced a result, an observation. It looks at those resulting observations and basically performs a majority vote. It picks the action sequence that leads to the most consistent outcome among the ones that actually executed successfully.
So it's choosing the path where the result seems most reliable based on trying a few valid options.
Precisely. The aim here is to significantly boost the robustness and reliability of the small agent's actions when you're actually using it. That self-checking adds a crucial layer of verification at inference time.
All right, so we have agent distillation as the core idea teaching the reason, act, observe cycle, and then two enhancers. First thought prefix, FTP, to improve the teacher's training examples, and self-consistent action generation, SAG, to make the student's actions more reliable in practice. So how did this combo actually perform? What did the experiments show?
They ran quite a comprehensive set of experiments. They used the Quinn 2.5 model family. The big 32 billion parameter one is the teacher, and then smaller students ranging from 0.5 billion up to 7 billion parameters.
Okay.
And they tested them on 8 different task benchmarks. These covered both factual reasoning, like question answering needing search, and mathematical reasoning, like complex word problems needing calculation. They also made sure to include both in-domain and out-of-domain tasks to really test generalization.
And the results, did teaching them to be tool-using agents actually pay off?
The overall results were, well, pretty striking. Agent distillation consistently boosted performance across every single student model size they looked at.
That's a good start.
And crucially, it significantly outperformed models that were trained using the traditional Code distillation method.
Yeah.
Especially, and this is important, on the out-of-domain tasks.
Ah, so that confirms the intuition, right? Learning how to use tools helps you generalize better because you're not just stuck memorizing specific reasoning paths you saw in training.
Exactly. You're learning a more fundamental, adaptable problem-solving skill. But here's the really remarkable finding, the headline result from the paper.
Yeah.
These agent-distilled smaller models, they managed to achieve performance that was comparable to, or in some cases even better than, Code-distilled models that were 2 to 4 times larger.
Wow. Well, hold on. Say that again. A small model performing like 1, 2 to 4 times its size.
Yes, the efficiency gains were huge. For instance, their 0.5 billion parameter agent-distilled model performed on par with the 1.5 billion parameter Code model.
3 times larger.
The 1.5B agent matched the 3B Code model. The 3B agent actually beat the 7B Code model. And maybe most impressively, the 7B agent model even outperformed the original 32B teacher model when that teacher was prompted using standard Code.
That is incredible. It really shows the power of embedding this interactive capability, this tool use, into much smaller models. They're punching way above their weight class.
Definitely. It allows them to leverage external capabilities instead of relying solely on internal parameters.
How did it break down for the specific task types, factual versus math?
Okay, so for factual reasoning tasks, the agent distillation method consistently outperformed even models trained with Augie-enhanced Code.
Augie being retrieval augmented generation, where you feed the model documents up front.
Right, and the agent approach did better because it's not just passively receiving documents at the start. It's learning to actively retrieve knowledge during its reasoning process whenever it identifies a gap. It makes the retrieval much more dynamic and targeted.
So it's not just getting the info dumped on it. It learns to go fetch it precisely when needed, mid-thought. That feels much more powerful.
It's more adaptive. And for mathematical reasoning, they also saw really strong gains, especially on the harder problems, like the AIM and Alimeth datasets. The agents clearly benefited from being able to offload complex calculations to the code tool.
Makes sense. Precise calculation is often a weakness for LLMs alone.
There was one interesting exception they noted on the Math 500 dataset with the 3B model, where the Code version sometimes did a bit better. They speculated this might be because the specific Quinn 2.5 models they used had already been heavily tuned on that particular dataset style using Code.
Ah, dataset contamination or alignment.
Potentially. But overall, even on math, the agent approach showed substantial benefits, particularly for harder problems.
Beyond the headline results, did they dig deeper into why these methods worked? Like, what was the specific impact of that first thought prefix, the FTP?
They did. They found that using FTP particularly boosted performance on the harder difficulty levels within the math tasks, like the level 4 and level 5 problems in the math benchmark.
Okay, so on the really complex stuff.
Yeah, which suggests that guiding the teacher to start with that more structured planning thought really helps the student agent learn how to break down and tackle more complex, multi-step reasoning problems. That initial planning structure seems key.
So that little nudge pays dividends when things get tough. Were there any downsides to FTP? Did it ever hurt performance?
Interestingly, yes, there was a nuance. They observed that on the factual tasks, using FTP sometimes led to the agent making fewer retrieval calls.
Fewer? Why would that be?
The hypothesis is that by starting with a more declarative, Code-like planning statement in its thought, The agent, especially a smaller one, might become slightly overconfident in its internal knowledge and less likely to recognize the need to actually go use the retrieval tool.
So it might try to reason internally when it really should be searching.
Potentially, yeah. Which could increase the risk of hallucination if its internal knowledge is wrong or outdated. It highlights this interesting trade-off. Structured thought is generally good, but not if it stops the model from using a tool when it's necessary.
That's fascinating. The way it starts thinking influences whether it even considers using a tool. What about the other method? Self-consistent action generation, SAG. How did that pan out in the analysis?
SAG performed exactly as intended. It was very effective at reducing errors when the agent tried to use the code tool. Their analysis showed it significantly cut down on both code parsing errors and code execution errors.
Making the code tool much more reliable for the agent.
Exactly. And this benefit was particularly noticeable for the smallest 0.5B model, which, as you'd expect, struggles the most with generating correct code on its own.
So SAG acts like a crucial quality control layer, making sure the agent's attempts to use tools, especially code, are actually viable and don't just crash the process.
Precisely. It boosts the robustness significantly. They also did an interesting comparison using models specifically trained for coding tasks, both as teachers and students.
And did using a code specialist model make the agent even better?
Surprisingly, it only had marginal impacts on the final agent performance.
Really? I would have thought a model with better inherent coding ability would be a stronger foundation for a code-using agent.
That's what you might intuitively think.
Yeah.
But the author suggests this finding implies the main bottleneck isn't necessarily the raw code knowledge itself,
Okay.
but rather it's learning how to effectively use the code tool within the agentic framework, learning when to call it, how to formulate the request based on the current reasoning state, and then how to integrate the result back into the thought process. Agent distillation teaches this orchestration skill.
So it's less about being a coding expert and more about being an expert tool user in the context of reasoning. That's a really neat insight.
It seems to be the critical factor, yes.
And efficiency is always a concern. Did turning these models into agents make them super verbose? Did they use way more tokens?
They looked at that too. They found that agent distillation didn't necessarily lead to a significant increase in token usage compared to standard core T models.
Oh, interesting.
On factual tasks, yeah, agents might use slightly more tokens because you have the back and forth with the retrieval calls, the query, the results.
That makes sense.
But interestingly, on math tasks, the agents often used fewer tokens
Fewer? How?
because they could offload complex or repetitive calculations to the code interpreter. Instead of writing out every single arithmetic step in the chain of thought text, they just generate a small piece of code, run it, and get the result. Much more concise.
So it balances out or can even be more efficient token-wise for calculation-heavy tasks. That's great news for practical deployment.
Absolutely. It's not just more capable, it's not necessarily more costly in terms of generation length.
Any other key insights from their deeper analysis?
Well, just reinforcing that point about retrieval calls, they did note that the larger agent models tended to make more retrieval calls than the smaller ones.
Suggesting they're better at figuring out when they need external info.
Potentially, yes. Better at judging when retrieval is needed, and maybe better at formulating the queries. And again, that finding about FTP leading to fewer retrieval calls on factual tasks really stands out. It underscores how the structure of the teacher's examples, those initial thoughts, is crucial for teaching effective tool use. There's delicate balance there.
Right, balancing structured thought with the willingness to reach out for external help. This whole approach feels like a really significant step forward. Taking these smaller, more practical models and giving them this dynamic ability to use tools, it seems way more powerful than just trying to cram more static knowledge or reasoning steps into them.
It really does feel like a powerful framework. The main takeaway that these agent-distilled small models can genuinely match or beat much larger CoT models, especially when generalizing, makes agent distillation look like a very promising direction for building capable, efficient, tool-using AI for real-world stuff.
Did they mention limitations or where this might go next?
They did. They pointed out the need to test this on other model families like Llama or Gemma to ensure the findings aren't just specific to the Qwen models they used.
Right.
They also noted that while agent distillation teaches tool use, it doesn't necessarily improve the model's core internal reasoning ability itself. So future work could look at combining this with other techniques, maybe reinforcement learning in these tool-using environments, to try and improve both aspects together.
Refining both the thinking and the tool use.
Exactly.
Yeah.
And as we saw with the FTP nuances, continuing to improve the quality and diversity of the teacher agent's trajectories used for the distillation is still an important ongoing challenge.
Okay, so pulling this all together for everyone listening, we've done a deep dive into this paper on agent distillation. It's a new method for training smaller language models. Instead of just teaching them to mimic the static reasoning steps of a big model,
It teaches them the dynamic reason-act-observe cycle. It teaches them how to actually use tools like information retrieval and code execution as part of their problem-solving process.
right, it goes beyond just distilling thoughts to distilling actions and interactions. And the big payoff is that this approach dramatically boosts the performance and, crucially, the generalization ability of these smaller models.
Allowing them to tackle problems needing external knowledge or calculation much more effectively, and enabling much smaller models to achieve results comparable to, or even better than, models several times their size trained with older methods like COT distillation.
It really shifts the focus, doesn't it? From trying to make the model know everything to making it skilled at finding and using information and tools when needed, learning an interactive problem-solving skill set.
Precisely. It's about leveraging external resources effectively.
So here's a final thought to leave you with. Considering how effective teaching models how to actively use these external tool search, code execution purrs to be, especially seeing those efficiency gains compared to just trying to distill more internal reasoning power. What does this suggest about how we should think about designing and training AI in the future? Should learning how to interact with the world, how to use tools, become just as fundamental, just as central as developing purely internal reasoning capabilities? It certainly makes you reconsider what truly constitutes intelligence and problem-solving ability in these systems.